Hello, I'm Michael O'Connell, and in tonight's video, we're going to be solving a problem in which we have fluid flowing through a non-circular pipe. On the board, I've drawn a rectangular channel in which fluid is flowing down through the channel at a volumetric flow rate Q. We're given the width, and we are also told that the channel is sloped with an angle theta with respect to the horizontal, such that fluid flows down through the channel. And we also see that this is an open channel. So the pressure at 1 and the pressure at 2 are the same, and there is no change in the cross-sectional area through which the fluid moves, so the velocity is also the same. So let's write out Bernoulli's equation. As I said, the pressure at 1 is the same as the pressure at 2, so this term is gone. And there is no change in the cross-sectional area through which the fluid is moving, so this term is also gone. We want to express this change in altitude. Notice that the altitude at 1 is higher than the altitude at 2, so this term would be negative. Now, we have this delta x term in the frictional heating expression, and that, of course, represents the length of our rectangular channel. So that's how we want to express the change in altitude. And we see here that that's given by this change here, which is delta x sine theta. So that will go right into here. And if you see that here, we have a delta x on both sides of the equation that cancels. Notice again, this delta z is negative, so that cancels with the negative sign on the other side, and I'll divide by 2 as well. So we have 2 times the fanning friction factor multiplied by the velocity squared divided by the diameter d. The next thing I want to talk about that is extremely important is the shear stress exerted on the walls. When solving problems with flow in non-circular pipes, we assume that the shear stress exerted along the walls is the same as it would be in a circular pipe for the same velocity. So we need to find the shear stress in a circular pipe to solve this problem so that we obtain the shear stress we assume is occurring when this fluid is flowing through our non-circular pipe, because it's our rectangular channel that we are dealing with here. So let's take a cross-section of fluid, this circular pipe, and it's completely full of fluid that's flowing downward, okay? And to obtain the shear stress, we can just perform a simple force balance. So we have the weight of the fluid downwards, and then we have the shear stress exerted along the wall upwards. So let's think about the weight of the fluid. We have the mass multiplied by the acceleration due to gravity. That would be the density multiplied by the volume multiplied by the acceleration due to gravity. We will express the volume in terms of delta x so that we keep the same length. Okay, so what would that look like? We would have the density, volume, so this would be area multiplied by delta x, and then we have g, the acceleration due to gravity. So this is the weight of the fluid, and this has to be balanced, of course, with the shear stress exerted along the walls. So to get at that force, we need the area over which that stress is exerted. So that includes the entire inner perimeter, which is wetted with fluid because it's full of fluid that's flowing downward. Okay, so this would be tau, which is your shear stress multiplied by that area. So that would be the wetted perimeter multiplied by the length, delta x. Excellent. So those terms cancel, and we get a very, very nice expression here. So we have rho g equals tau, and then we have the wetted perimeter over the area. So what we are going to do now is actually find what this is equal to. And I will make a quick note of it. It's not relevant to this video, but the inverse of this term here is what's called the hydraulic radius. And that's pretty much all I'm going to say about that, because it's not the main focus of my video here. But what I do want to find is what this actually is. So the wetted perimeter, that is the circumference, right? Because it was full. So that's pi over d. And then our cross-sectional area, pi d squared over 4. So this becomes, cancels, 4. Because it's a denominator, in the denominator it becomes a numerator. So we have 4 over d, okay? So pay attention there, I'm going to move this over here. And this is really nice, because now we can divide both sides by the density rho, and we can just plug this in for g right here. Now let's write out our expression for the shear stress for a circular pipe. So we've moved this over here, so we have 4 times tau over rho d multiplied by sine theta equal to this right-hand side. So we get these diameters to cancel out, and then we multiply both sides by rho, and then we divide by 4, so we get this expression for the shear stress. This would be the fanning friction factor multiplied by the velocity squared multiplied by the density, all divided by 2 sine theta. Awesome. That is very, very important. Why is that important? Well, we're going to use it again, right? So I'm going to erase some things to give us some room. But the key difference here, which makes a lot of sense, is that, well, when looking at our rectangular channel, our wetted perimeter is different. So that's what we need to think about here. So we need this because we are assuming that the shear stress is the same for the same velocity in our rectangular channel. So what did we have? We had rho times g, and then we had tau multiplied by the wetted perimeter over the area. So it's this ratio that we need for the rectangular channel. What's the wetted perimeter? Let's look at this view. Okay, so we just have the height on both sides there. So it's 2h plus the width. Okay, all of that is in contact with the surface there. Okay, so we need that. And then we have the area. The area is easy. That's just h times w. Okay, so this goes into there, and then that's multiplied against that. So let's express this over here. So we have rho g equals tau. I should write tau, actually. That's the whole point. 2 sine theta. Then we have the wetted perimeter. So we have the 2h plus w over hw. Okay? These cancel out. And this is great. So we have an expression for the acceleration due to gravity. And this is something that we can use when we solve this problem numerically in Python. And you probably know what I'm going to do. We have one unknown, which is the height of the fluid level for our fluid that is moving down through this channel. This is the unknown that we want to solve for. And we can do a root solver on this, right? We can find the value of the fluid height that makes the difference between the acceleration due to gravity, 9.8 meters per second squared, and our expression, where the root solver adjusts values for the fluid height. We can, the root solver will find the value of the fluid height that makes that expression equal to 0. Okay, now what else do we need, right? We're not done yet. We've seen this guy before. This guy's always a problem. We'll get to him in a second. The problem, aside from just talking about the fanning friction factor, is actually we're given the volumetric flow rate. So we do want to follow the rules here and follow the problem, right? So the volumetric flow rate is the velocity multiplied by the cross-sectional area. This cross-sectional area for a rectangular channel, remember, back to the rectangular channel, I think this problem can be quite confusing. At least it was for me a little bit the first time I encountered this, because you're jumping from circular to whatever other non-circular pipe you're dealing with. So I know that can be hard to follow along, but again, we're talking about the volumetric flow rate through the rectangular channel, so we use that cross-sectional area, h times w. And here we obtain this expression for the velocity, right? Where we have, hopefully I didn't mix it up, but yeah, the volumetric flow rate divided by the area. Okay, so that goes into there. And let me just erase all of this and rewrite it, and we can see what expression we'll have. So I got a little too excited there. This is the actual expression we'll have for g in our function that we use the root solver for. And let's see, that goes into v squared, so we're going to have f q squared. And then the rho is gone, so we don't have to worry about that. But you do have 2 sine theta. And we would have hw cubed and 2h plus w here. And I'll get rid of all this junk that's in our way. Excellent. So this is the equation. I'm not lying to you this time. This is the one that we're going to use. Okay. Because we were given the volumetric flow rate in the problem, and I want to follow the problem that was given to me. So the fanning friction factor, that is always something we have to concern ourselves with, right? Because it takes in the Reynolds number. We're going to use the Churchill equation function that we used in a previous video. So the coding part should go pretty fast. And this is rho Vd over mu. We should have this memorized, okay? So we have the diameter. That's what we're after here. That is extremely important. Because you're looking at this problem and you're like, there's no diameter for your rectangular channel. And once again, we are going to find the effective diameter using this ratio we found, which was the ratio of the wetted perimeter to the area for a circular pipe. We're going to use that and equate it to the ratio for a non-circular pipe, in this case, our rectangular channel. So what's that going to look like? Well, we have 4 over d. And then the wetted perimeter for us is 2h plus w over hw. Okay? So what's our effective diameter? That would be 4hw. This is solving for d, obviously, over 2h plus w. So this also needs to be in our function, and it actually needs to be in a line right before we have our Reynolds number expression. And then we can have our Churchill equation function embedded in our function that we're going to perform the root solver on. Okay, we're getting kind of lazy there because it's just so much easier to use that code that we've already written. And the Churchill equation is really special because we can use it to find the fanning friction factor for laminar flow and turbulent flow. So there's just less concern for us when we're doing these types of problems, which is extremely nice. And like we did, I think, in the video in which we used that Churchill equation when we were doing all the pipe flows, we are going to use the surface roughness of like 1 times 10 to the negative 6th. But other than that, we are ready to go. These are the equations that we need to know, right? So we have the effective diameter, our equation for the acceleration due to gravity. This is the basis for the root solver that we are going to be using. Again, we will have the Churchill equation function that we've used before in the past, and then obviously the expression for the Reynolds number is needed as well because we have our expression for the effective diameter. So I think we are ready to find the answer to this problem and see what fluid height we have for this fluid that's moving through this rectangular channel. Now we're ready to find the height of the fluid that is flowing through our rectangular channel. Here we are going to use numerical Python in the root solver, as well as code that I used in a past video, which you can find in my third transport playlist. So I have the density of water, the viscosity, and the acceleration due to gravity, as well as the Churchill equation function, which takes in the Reynolds number and the surface roughness and returns the fanning friction factor, which we will need. In this problem, we were given the flow rate, which is 1 cubic meter per second. We were also given the width of the channel, which was 0.5 meter, and the angle. Now we're ready to define our function. This function will take in a vector of unknowns. The unknown we are solving for is the fluid level in the rectangular channel. So we extract the first element. Then we define the effective diameter for the rectangular channel.
The Reynolds number is rho Vd over mu, where the velocity v is the quotient of the volumetric flow rate in the cross-sectional area. The fanning friction factor is obtained from the Churchill equation, where we supply the Reynolds number and the surface roughness, which is 1 times 10 to the negative 6th. And this function returns the difference between the acceleration due to gravity and the expression which we have for the acceleration due to gravity, which I'm going to type in right now. Before we try to find the height of the fluid flowing through our rectangular channel, let's check our code. So we have the height that we're trying to find, the effective diameter of the rectangular channel, and the Reynolds number, which is rho Vd over mu. And I forgot mu, which is the viscosity. So I need to put that in here. We have the fanning friction factor, which we obtained from the Churchill equation, and then this expression for the acceleration due to gravity, which we got from our work on the whiteboard. So now we can use the root solver, where we supply our function and an initial guess, which will do 0.2 meters. We extract the solution element and we take it out of the vector. And we obtain 0.14 meters for the height of the fluid flowing through our rectangular channel. So I hope you see the practical necessity of what I've covered in this video. Specifically, we're dealing with flow in non-circular pipes. So I thank you so much for watching, and I hope to see you next time.